In this videotape, we're going to be discussing continuous functions. Let's start with the definition of continuity. A function f is continuous at the number a if the following three things hold. First of all, f of a exists. That means f has to be defined at a. Secondly, the limit of f of x as x approaches a exists. The function has to have a limit at a. And third, the limit of f of x as x approaches a has to be f of a. Not only does the function have to be defined and the limit exists, but the limit of the function at a has to be what the function is defined to be at a. Okay, now some books only use condition 3 as the definition of continuity, and that would be correct. Because after all, if the limit of f of x as x approaches a equals f of a, that does imply that f of a exists, that the limit exists, and of course that they're equal. Okay, but I prefer to break it up into these three parts so that as we examine various functions for continuity, we will be able to see exactly what condition is violated or if all three conditions hold. Now notice that the definition is done at a point-by-point basis, where if this holds at the number a, we see the function is continuous at the number a. If a function is continuous at every number on the interval, then we'll say the function is continuous on the interval. Okay, let's start by looking at the first example. The function f of x is x squared minus 4 over x minus 2. And the question is f continuous at the number 2? Okay, here we have a function. Now, what is the domain of this function? The domain of this function is all x, but not 2. Okay? We're worrying about division by 0 or, say, square roots of negative numbers. Here we only have to worry about division by 0. And we see that if x is equal to 2, we would have division by 0. So the domain of f would be all x values, but not 2. We have the question, is f continuous at 2? Now, if you remember our definition, the first part of the definition is that f of a has to exist. That is, f of 2 has to exist. Well, f of 2 does not exist. F is not defined at 2. If we try to substitute x equals 2 in here, we'd have division by 0. F of 2 does not make any sense. F of 2 does not exist. 2 is not in the domain of the function. Since f of 2 does not exist, condition 1 is violated. In the continuity definition, and f is not continuous at 2. It would be interesting to sketch the graph of this function f. F of x is x squared minus 4 over x minus 2. If we were to factor the numerator, we'd have x plus 2 times x minus 2 over x minus 2. Now, we would like to cancel the x minus 2's. However, if we were to do that, it would look like the function f of x is x plus 2. But that's no good because we know the domain of f is all x but not 2. And over here, we wouldn't see that anymore. So we can cancel so long as we make it very clear that x is not equal to 2. After all, when you're canceling, you're dividing. We're going to divide numerator and denominator by x minus 2. We're assuming x minus 2 is not 0. We're assuming x is not equal to 2. So if you want to reduce this to f of x equals x plus 2, that's OK, so long as you make sure that you specify that now the domain is all x but not 2. It wasn't necessary in the original statement of the function because it was clear to anyone who looked at this that 2 is not in the domain of the function because you'd have division by 0. If you're going to reduce it to x plus 2 like this, it's no longer obvious that 2 is not in the domain of the function, so you have to state it explicitly. You have to say f of x is x plus 2 so long as x is not equal to 2. these two functions are the same. So if we want to sketch the graph of this function, we can instead sketch the graph of this. And this, of course, has as its graph a straight line, except there's some problem at x equals 2. Let's see what happens. This is, what would y equals x plus 2 look like? Well, if x is 0, y would be 2. And if y is 0, x would be minus 2. Okay, it would be a straight line. Look something like that. It's supposed to be a straight line. Have a little imagination here. Now, that would be the graph of y equals x plus 2, but 2 is not in the domain of this function. So when x equals 2, there should be a hole in the line. So the graph of the function f, straight line y equals x plus 2, except there is a hole at the point 2, 4. See if I can just straighten this out a little. Like a little bit. Okay, so the graph of f, it's a straight line with a hole at 2, 4, and we see that the function is not continuous at 2. The function is not defined at 2. It violated condition 1 of the continuity definition. And for the function to be continuous at 2, f of 2 would have to exist, and f of 2 does not exist in this example. For our next example, let's look at the following. The function g of x, I want it to be equal to 1 over x if x is not equal to 0, and 3 if x equals 0. And the question now is g continuous at 0? Okay, well, according to the definition of continuity, the first thing we'd have to check is, does g of 0 exist? According to this definition, g of 0 is equal to 3. So condition 1 is okay. For the function to be continuous at 0, it would have to be defined at 0. Okay, now if this function had just been g of x was equal to 1 over x, that would be the hyperbola. The graph would look like this, would be the hyperbola in the first and third quadrants, like so. And the domain of this would be all x but not 0. This function says, look, I know 0 is not in the domain of the function. So take that function when x is not equal to 0, and when x equals 0, let y equal 3. So this is the graph of the function g of x. It's all x. G of x for, it's 1 over x if x is not 0, and when x is equal to 0, y is equal to 3. So in answer to the first question, is it defined at 0? Yes. It wouldn't have been unless you had the second part of the definition. With the second part of the definition, it's true that 0 is not in the domain of the function 1 over x, but here we say, okay, you can't plug in here 0, but we're telling you if x is equal to 0, y should be 3. So g is defined at 0. However, we are going to have a problem with the second part of the continuity definition. What about the limit of g of x as x approaches 0? As x approaches 0, x is not equal to 0. It's just getting close to 0. So in this case, g of x is 1 over x. Now, the limit of 1 over x as x approaches 0, this limit does not exist. It's a situation where the bottom is going to 0 and the top is not. Such a limit does not exist. If we look geometrically, let's look over here at the graph. As x approaches 0 from the left side, the y values are getting increasingly negative. As x approaches 0 from the right side, the y values are getting increasingly positive. It is clear that the limit as x approaches 0 does not exist, since the limit as x approaches 0 from the left certainly does not equal the limit as x approaches 0 from the right. In fact, each of those limits don't exist. But at least from the left, we could say that the limit approaches minus infinity, and from the right approaches plus infinity, but the limit does not exist at 0. And later on, we will have a simple theorem that tells us if the bottom is going to 0 and the top isn't, that limit will certainly not exist. Okay, so this condition is violated. Condition 2 is violated. It was defined at 0. It wasn't as simple as the first example that we had, where you could just say the function is not defined. It was defined, okay, but the limit did not exist at 0. Okay, so is G continuous at 0? No. G is not continuous at 0. Because condition 2 is violated. For our third example, let's try this. H of x equals x squared minus 4 over x minus 2 if x is not equal to 2, and 1 if x does equal 2. And the question here is H continuous at 2? Okay, let's check. Condition 1. Does H of 2 exist? Yes. H of 2 is equal to 1. Condition 1 is okay. There would be a problem substituting 2 into this first part, but we're told that's only if x is not equal to 2. If x equals 2, h of x is equal, or h of 2 is equal to 1. So, yes, h is defined at 2. Condition 2. Does the limit of h of x as x approaches 2 exist? Well, as x approaches 2, x is not equal to 2. If x is not equal to 2, the function is x squared minus 4 over x minus 2. All right? To find this limit, we could realize that x squared minus 4 factors into x plus 2 times x minus 2. And as x approaches 2, remember x is not equal to 2, it's just getting close. Therefore, x minus 2 is not 0, and we can divide numerator and denominator by x minus 2. Now, this would be the limit of x as x approaches 2 plus the limit of 2 as x approaches 2. From our limit theorems, we know the limit of x as x approaches 2 is 2. The limit of a constant is just that constant. 2 plus 2 is 4. So yes, the limit of h of x as x approaches 2 does exist, and in fact, it's equal to 4. Condition 2 is okay. Condition 3, however, gives us a problem. Condition 3, we go back over here, tells us the limit of the function as x approaches a has to be what the function is defined to be. That doesn't work out. In other words, we have the function defined, we have the limit existing, but the answers to 1 and 2 have to be the same. That's what condition 3 is saying, and that's not what we have here. The limit of h of x as x approaches 2 is 4. So the limit of h of x as x approaches 2 does not equal h of 2, because the limit is 4, and that's not equal to what it's defined to be, which is 1. So condition 3 is violated, and the answer to the question is h continuous at 2. The answer is no. Condition 3 is violated. It is not continuous at 2. So we've seen an example of condition 1 being violated, where we had like the line with a hole in it. We saw an example where the function was simply not defined. We saw an example of condition 2 being violated, where the limit did not exist. And now we have an example of condition 3 being violated. Let's sketch the graph of this function h. We have, as before, we have the line, basically, y equals x plus 2, if x is not equal to 2. In other words, if x is 0, y is 2. If y is 0, x is minus 2. So just like before, we had that line with the hole in it at 2, 4. That's what the first part is saying. If x is not equal to 2, we're talking about the line with the hole in it. Except now it says if x equals 2, y is equal to 1. So this is what it looks like when condition 3 is violated. And condition 1 and 2 are all right. We have the function defined. We have the limit existing. The road from the left and the road from the right are coming together here. But where the roads come together, what the limit is not what the function is defined to be. We sort of have like a misplaced point. If the function's defined, it has a limit. As x approaches 2 from the left or from the right, the y values are getting close to 4. Okay, so the limit exists, it's 4. It's defined to be 1. The limit is not what it's defined to be. So we have like this misplaced point. And this function is not continuous at 2. Now we've been using this definition to determine whether or not a function was continuous at a certain number. Okay? As I mentioned earlier, if a function is continuous at, say, every number at an interval, we would say the function is continuous over that interval. Now, geometrically, what would a continuous function look like? Okay, if a function was continuous throughout its domain, its graph would be unbroken. You'd be able to draw it without ever taking your pen off the paper. There would be no holes, no breaks, no jumps, no gaps. Okay? The graph of a continuous function would be an unbroken curve, okay, with no holes, no breaks, no jumps, no gaps, and you could draw it without ever taking your pen off the paper. Okay, now, we have been thus far using this definition to determine whether or not a function was continuous at a particular number. Let's consider it the other way. Suppose I knew that a function was continuous, say throughout its domain or on certain intervals. If I knew a function were continuous at, say, a certain number a, then, of course, this definition would hold. In particular, part 3 would hold. Okay? Well, if part 3 holds, what does that say? If I knew a function were continuous, then I know part 3 holds. It tells me the limit of f of x as x approaches a is f of a. Now, we have been using that to determine whether a function is continuous, but if I knew the function was continuous, then this would hold true. And what does this say? This says you want to find the limit of this function as x approaches a. You don't have to use all those complicated limit theorems that we studied in class. We can simply substitute a into the function. This says if the function is continuous, then the limit of f of x as x approaches a is f of a. Okay? Actually, this definition is an if and only if. If the function is continuous, this holds true. If this holds true, it's continuous. So we've been saying if this holds true, it's continuous, but it also works the other way around. Okay, if it's continuous, then this holds true. In particular, if a function is continuous at the number a, you can find its limit at a by substitution. And this will eliminate the need of the use of many of those limit theorems. For continuous functions, limits can be found by substitution. So it would certainly be to our advantage if we had a whole bunch of functions that we knew were continuous. And in fact, it's exactly what we can do. Let's consider it. Remember, a continuous function is one whose curve is unbroken. Because of that, the function, let's say, f of x equals x, the identity function, y equals x. That's a straight line going through the origin, and 1, 1, and 2, 2. It would look something like that. This is certainly the graph of a continuous function. The identity function, y equals x, is continuous. Also, constant functions are continuous. For example, g of x equals a constant, like g of x equals 4, or y equals 4. The graph would be a horizontal line, y equals 4, y equals 5, y equals minus 2. All of those functions would be continuous. Any constant function would be continuous because the graph would simply be a horizontal line. So if all constant functions are continuous throughout their domain, actually from minus infinity to plus infinity, and the identity function is continuous from minus infinity to plus infinity. Okay? Those are the basic building blocks we need to show that various functions are continuous. We have a theorem that says if two functions are continuous and you add them together, you produce another continuous function. Similarly, if you subtract them or if you multiply them, you'll get a continuous function. So by using the fact that all constant and all constant functions and the identity function are continuous on minus infinity to plus infinity, I could, for example, show that all polynomials are continuous on minus infinity to plus infinity. Let's look at a polynomial like 4x cubed plus 3x squared plus 7x plus 2. We could think of this as four functions being added together. The last one, y equals 2, is certainly a continuous function. The third one is the product of two continuous functions, y equals 7 and y equals x, a constant and an identity function. You take a continuous function, you add it to a continuous function, you produce a continuous function. Similarly, the second function here is the product of three continuous functions, y equals 3, y equals x, and y equals x. So that's continuous. Add it to a continuous function, it's continuous, and so forth, to show that all polynomials are continuous throughout their domains, which are, in fact, minus infinity to plus infinity. Furthermore, the theorem goes on to say that not only can you add, subtract, or multiply two continuous functions and produce a continuous function, you can divide two continuous functions and get a continuous function so long as the denominator is not 0. So if we have a rational function like big F of x is x cubed plus 4x squared minus 5 over x squared minus 9. This function will be continuous so long as the denominator is not 0. It's a rational function, the quotient of two polynomials. It's continuous so long as the denominator is not 0. So it's continuous everywhere except at 3 or minus 3. So should you want to find the limit, for example, of this function as x approaches 7, you would know that this function is continuous at 7 because it's continuous everywhere except 3 and minus 3. You'd be able to find the limit by substitution. Okay, so we have quite a few functions that are continuous, and as such, you can find their limits by substitution. All polynomials are continuous on minus infinity to plus infinity. Rational functions are continuous so long as their denominator is not 0. And in fact, the algebraic functions that we'll be dealing with in class are basically continuous wherever they exist. Now, this does not apply to split functions. I'm talking about a function that is defined by simply one equation. If we want to consider a continuity of split functions, we're going to have to spend a little bit more time. Let's look at an example of a split function. This would be example 4 on this tape. Let's look at the function f of x is equal to x plus 2 if x is less than minus 1, x squared if minus 1 is less than or equal to x is less than or equal to 2, and 4 minus x if x is greater than 2. Now, we're interested in determining if this function is continuous, say, on minus infinity to plus infinity. Okay. Is f continuous on the entire real line? Does that mean we're going to have to check every single real number? using the definition of continuity to see if the function is continuous? No, we won't. We'll look to see how this function is put together. This split function is composed of three functions. Y equals x plus 2, y equals x squared, and y equals 4 minus x. Each one of these, by themselves, would be continuous on minus infinity to plus infinity. The first and the third have as a graph straight lines, and the middle one is a parabola. Let's see. If x is 0, y is 2. If y is 0, x is minus 2. This function by itself would look like that. That's the line y equals x plus 2. Now, y equals x squared would be a parabola, vertex at the origin. Goes through 0, 0. It would go through 1, 1, minus 1, 1, 2, 4, minus 2, 4, and so on. It would look something like that. And y equals 4 minus x. Once again, its graph is a straight line. If x is 0, y is 4. If y is 0, x is 4. We have something like this. Now, by themselves, each one of these functions would be continuous on the entire real line. Y equals x plus 2, y equals x squared, y equals 4 minus x. Either you could say, well, you can draw their graph without ever taking your pen off the paper, or of course they're polynomials, and as such are continuous on minus infinity to plus infinity. So basically, the question that is f continuous on minus infinity to plus infinity really comes down to, is f continuous at minus 1 and at 2? Because what we're going to do is a cut and paste job on these functions. We're going to take part of this function, part of this one, part of this, put them together, and let's see if the final result is continuous. So the only questionable spots would be these breaking points, minus 1 and 2, when you stop following one curve and start following the other curve. And that's what we have to determine. Okay, now, you could sketch it and try to determine it that way. Let's try to first do it from just the definition of the function, and then we'll put the final picture together to confirm our answer. Okay, let me rewrite the function over here. So we'll have it x plus 2, x squared, and 4 minus x. So what we have to determine is f continuous at minus 1, and is f continuous at 2. Every place else is all right. So the only question is minus 1 and 2. First, is f continuous at minus 1? We have to find out about f of minus 1, does it exist? And then we're going to have to look at the limit of f of x as x approaches minus 1. And if each of these exists, they have to also match. That's what condition 3 says. Let's see. F of minus 1. If we want to know what y is when x is minus 1, we follow and see it's the middle part of the definition. That has the equal sign. That tells us what to substitute in for f of x when x equals minus 1. F of x is equal to x squared. So it's minus 1 squared, which is plus 1. Now, to find the limit of f of x as x approaches minus 1, since we have this split at minus 1, we're going to have to look at the limit of f of x as x approaches minus 1 from the left, and the limit as x approaches minus 1 from the right. And what we have to do here is to examine See which part of the function gets substituted in for f of x. That's the whole trick here. We have our number line. We're breaking the function at minus 1 and 2. If we break the function at minus 1 and 2 here, we break the number line into 3 intervals. 1 where x is less than minus 1, 1 where we're between minus 1 and 2, and 1 where we're greater than 2. Now, if we're approaching minus 1 from the left side, minus 1 from the left side, we're in the region where x is less than minus 1. So naturally, f of x is to be replaced by x plus 2. So as x approaches minus 1 from the left, replace f of x by x plus 2. Because as you approach minus 1 from the left, you are less than minus 1. So the function should be x plus 2. When we want to find the limit as x approaches minus 1 from the right, when you approach minus 1 from the right side, we'll be in the region between minus 1 and 2, and therefore we'll replace f of x by x squared. Now, each of these limits can be found by substitution because these are just polynomials, and we know the limit of a polynomial can be found by substitution. So if we want to find out what happens as x approaches minus 1, we can let x be minus 1, minus 1 plus 2, and that's 1. Here we let x be minus 1, we get minus 1 squared, that's 1. Since the limit from the left is 1 and the limit from the right is 1, then the limit of f of x as x approaches minus 1 is also 1. So condition 1 holds. The function is defined at minus 1. Condition 2 holds. The limit does exist at minus 1. And condition 3 holds because the limit of f of x as x approaches minus 1 equals f of minus 1. The answer here is the same as the answer here, so condition 3 holds. So is f continuous at minus 1? The answer is yes. Now let's look and see what happens at 2. Once again, we're going to map it out the same way. We're going to find f of 2 and look at the limit of f of x as x approaches 2. And if they're the same, then we'll say it's continuous. Well, what is f of 2? To find f of 2, we look to the part of the function that has the equal to, and we see f of x is x squared, f of 2 is 2 squared, or 4. In order to determine the limit of f of x as x approaches 2, because it is a split function, and there is this break at 2, we will have to look at the limit of f of x as x approaches 2 from the left, and the limit as x approaches 2 from the right. Now, the only question is what part of the function gets substituted in for f of x? Well, as x approaches 2 from the left side, as you approach 2 from the left side, you're in the minus 1 to 2 region. So for f of x, replace x squared. As you approach 2 from the right side, here is 2. From the right side, you're in the x greater than 2 region. So substitute for f of x 4 minus x. So the trick is just to know what to replace f of x by. Now, these limits can be found by substitution because these are continuous functions. They're just polynomials. So here we'd get 2 squared, or 4. Here we get 4 minus 2, or 2. Okay, apparently the limit of f of x as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. Therefore, the limit does not exist. So condition 1 was okay, but condition 2 was violated. And the answer, is f continuous at 2? No. So where is this function continuous? The question originally was, is this function continuous on minus infinity to plus infinity? It is not. It is not continuous at 2. We did not have to check every point. We knew we were basically all right, except at minus 1 and 2. They had to be checked separately, and we did. And we found that at minus 1, the function was continuous, but at 2, it was not. Okay? F is continuous everywhere except at x equal 2. Continuous for all x, but not at 2. Now let's see what the function f of x looks like. We have each function sketched separately, so it should be a very simple matter to come with our scissors and cut off pieces of each of these. Well, if x is less than minus 1, we're to be following the line y equals x plus 2. Let's come with our scissors and cut it at x equals minus 1. And let's cut the graph of y equals x squared at x equals minus 1, and then at x equals 2. This is minus 1, this is 2. And then finally, let's cut the graph of y equals 4 minus x at x equals 2. And we're told to take the leftmost portion from this line, take this portion from this line, the middle portion from the parabola, and the rightmost portion from this line here. Now, on the parabola, we actually take the values for minus 1 and for 2. This is minus 1, 1. This is 2, 4. We follow the first line up to, but not including, x equal to minus 1. So there's a hole at minus 1, 1. And the last line, we start following when you're greater than 2. So we do not include the point 2, 2 here. Okay, putting this all together, we produce the following picture. Let's see what we have. We have the line y equals x plus 2. We take it up to, but not including the point, minus 1, 1. And it would look like so. Supposed to be a straight line, something like that. Then we take the parabola. Now, the parabola did start at minus 1, 1, so it fills in this open circle here, and we take it from minus 1, 1 up to and including the point 2, 4. But then we start, when we're greater than 2, we start on this line y equals 4 minus x, which starts at 2, 2 with an open circle here, and then continues on down. So we can see that this function was continuous at minus 1, which is what we found out, but it was not continuous at 2. There was no problem. We knew each individual function was all right. The question is, when we came and cut and pasted them, took a part of this, part of this, part of this, and put them all together, what would happen? And you can answer this either from the sketch, or as we saw over here, you can do it completely without the sketch, just using the equations. But regardless, we see that the function was continuous at minus 1. The limit did exist, and the function was defined to be 1. That's what the limit was. Everything was fine. But at 2, the function was defined to be 4. However, the limit did not exist. The limit from the left was 4, and the limit from the right was 2, and they did not match. So the limit did not exist and was not continuous at 2. This function is continuous everywhere except at x equals 2. For our last example, let's try the following. I want you to find C so that the function g will be continuous on minus infinity to plus infinity, where the function g is defined to be the following split function. G of x is cx squared if x is less than or equal to 2, and cx plus 2 if x is greater than 2. I want to find the number c to make this function continuous throughout its domain, throughout the real line. Okay. Now, this is a split function. Y equals cx squared is a parabola. Since we don't know if c is positive or negative, we don't know if the parabola is opening upwards or downwards, but we do know it's a parabola, and it should be continuous throughout the entire real line. Similarly, y equals cx plus 2 is a straight line. It also is continuous on minus infinity to plus infinity. Either you can do it from their graphs, or you can say, look, these are both polynomials and there's no problem. They're continuous functions. So the only question, if I want this function to be continuous on minus infinity to plus infinity, the big question is, well, it's got to be continuous at 2. Because 2, it's a split function, and that's when you stop following one part of the function and start following the other. And as we saw in the preceding example, okay, in order for this function to be continuous at this breaking point, we have to have the definition of continuity holding. In particular, the limit at 2 has to exist. Okay, so we don't have to worry about any place except 2. We understand that the parabola, the straight line, on their own would be continuous everywhere. It's just that we're going to follow the parabola up to and including 2, and then we're going to switch to the straight line. And the only way it's going to be continuous is if it's continuous at 2. Okay, now, to be continuous at 2, the limit, okay, for g to be continuous at 2, the limit of g of x as x approaches 2 must exist. Okay, in order for g to be continuous at 2, which is our only trouble spot, the limit of g of x as x approaches 2 exists. As x approaches 2 from the left, and the limit of g of x as x approaches 2 from the right, each have to exist, and of course they have to have the same value, and then the limit of g of x as x approaches 2 will exist. Okay, we want the limit of g of x as x approaches 2 to exist. For g to be continuous at 2, we want the limit of g of x as x approaches 2 to exist. For that limit to exist, okay, the limit of g of x as x approaches 2 from the left has to exist. The limit of g of x as x approaches 2 from the right has to exist. And these two have to be equal. Okay, that'll make sure that the limit exists. And then we'll worry about if it's defined at 2. We need the first, I've jumped right to the second condition of continuity. We'll worry about the first one after we determine what c is. Okay, the limit as x approaches 2 from the left. As x approaches 2 from the left, x is less than 2. In other words, here we have our real line. This side x is less than 2, this side x is more than 2. As x approaches 2 from the left side, x is less than 2, and the function is cx squared. As x approaches 2 from the right side, When you approach 2 from the right side, you're greater than 2, and the function is cx plus 2. Now, how do we find the limit as x approaches 2? Since this is a parabola, we know it's a continuous function. We can find the limit by substitution. We can simply let x equal 2. Be careful, okay? You have the 2 letters, but x is approaching 2. We'll let x equal 2. It'll be c times 2 squared, or 4c. As x approaches 2 from the right, once again, we're going to let x equal 2, and we'll get c times 2 plus 2, or 2c plus 2. Okay, in order for the limit of g of x as x approaches 2 to exist, the limit from the left and the right have to match. So 4c has got to be equal to 2c plus 2. Okay, the limit of g of x as x approaches 2 from the left has got to be equal to the limit of g of x as x approaches 2 from the right. If these things are equal, then we can say the limit of g of x as x approaches 2 exists. Well, these will only be equal if, subtracting 2c from both sides, 2c equals 2, dividing by 2 if c equals 1. Let's see what happens. If c equals 1, then the limit from the left would be 4 times c, 4 times 1, or 4. The limit from the right would be 2 times 1 plus 2 would be 4. Since the limit from the left and the limit from the right would be the same, the limit of g of x as x approaches 2 would be 4. Furthermore, g of 2, okay, would be equal to 1 x squared, or 1 times 2 squared would also be equal to 4, and therefore the function would be continuous at 2. So in order for g to be continuous at 2, one of the things we knew had to happen was a limit as x approaches 2 of g of x had to exist. The only way that limit could exist is if the limit from the left and the right were the same. That led us to these two equations. We had the limit g of x as x approaches 2 from the left was 4c. The limit of g of x as x approaches 2 from the right was 2c plus 2. We knew that those two limits had to be the same. That led us to the value for c. Now that we know the value for c, let's see what we have here. The function g of x, we now know c has to be 1, is 1x squared if x is less than or equal to 2, and 1x plus 2, or x plus 2, if x is greater than 2. G of 2 is equal to 4. The limit from the left as x approaches 2 is 4. The limit from the right as x approaches 2 is 4. So the limit of g of x as x approaches 2 is 4. It's defined to be 4, so we're all set. If you want to sketch the graph of the function, now that we know what c is, we have y equals x squared up to and including the point 2, 4. And then we start following the line y equals x plus 2, which does go through the point 2, 4, and has slope 1, and it looks something like this. So y equals x squared up to and including 2, 4, and then starting right after 2, 4, we're on the line y equals x plus 2. But this also would go through 2, 4. And it would go through, for example, 3, 5, and that gives us the tilt that we need. And now we have found c, so this function g will be continuous on minus infinity to plus infinity. And that brings us to the end of this tape.